Welcome back everybody. This is our 11th class in JEE mains previous year questions for chapter moving charges and magnetism of class 12th. Before this video we have made several videos in this series and all of those videos are available on our YouTube channel's playlist section. We have also started similar series for NEET previous years, so you can find those videos also in our channel's playlist. And if you find these videos helpful, useful, then do press the like button, share them as much as possible, and subscribe to our channel. Your share and subscribe help us a lot to grow. Also, if you want to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any donation, however small it may be, will be highly appreciated. So with this, let's start today's video. And in the previous one, I think we are around at 70 or something, question number. This was the last question which we covered. And we will start with the next one. So a ridged square loop of side A carrying current I2 lying in horizontal surface near long current I1 carrying wire in the same plane as shown in the figure. The net force on the loop due to the wire will be. Now, as we can see from the diagram, that this is a square form of loop and this is a wire, and both are in the same plane. And according to the, we can say, Biot-Servet law, we know that dB is equal to magnetic field due to any small element is mu node by 4 pi d, not d, we will use r here, I dl across r divided by r square. So here this dl vector is the direction of the current and r is the distance vector. And suppose here in this case of this square, we can say A, B, C, D. We have four conductors on which we have to find out the value of force acting on it. We have to find the force on AB, on the BC, on the CD, and on the DA. Only then, after adding those all forces, we will be able to find that there is repulsive force or attractive force. Now, for magnetic field to exist by a charged particle at any point, so what we will do here, first we will find the value of magnetic field along these conductors, and then we will find the force experienced by these conductors. So let's start with the CD and AB, because for AD and CD we know the formula, because as they are, we can consider them as a parallel conductors, two parallel conductors with I. Let's say this is conductor X. So conductor X and conductor AD are parallel conductors with current flowing in the opposite direction, so they will repel each other. And conductor X and conductor CD are the parallel conductors with current flowing in the same direction, means they will attract each other. And we also know that value of magnetic field at point AD will be different as compared to the value of magnetic field at CD. So forces will be different. Now coming to the CD and AB, we cannot have a single value of magnetic field, because for a wire we know that value of magnetic field is given by, for a wire or infinite conductor, the value of magnetic field is given by mu node by 2 pi into I by T. This is the value of magnetic field due to a long, infinitely long conductor at any point at some distance d from it. Now, for AD, we can take a mean distance between the a point between A and D, and that will give us the value of magnetic field. But regarding AB, as distance between A and B is variable, distance from A to B is increasing, then value of magnetic field will also keep on changing. Means A to B value of magnetic field is variable. So it will become difficult to find the force acting or to find the magnetic field acting on the AB. But as we also know, formula for the force on a current carrying conductor is given by I L cross B, where B is the direction of the magnetic field and I is the current and L is the length vector, or we can say direction vector. Now let's do calculation for first for the AB. For AB, as we can see that direction of current is in positive x direction, so direction of length vector will be also in the positive x direction. So I, as it is the I2, I2 is the value of current flowing in the AB as per the diagram. Now direction of the length vector is positive x according to direction of the current. So suppose side is A, so A times I cross. The value of magnetic field is not known to us because magnetic field is variable here, but we take a we can say a random value of magnetic field, some averaged out magnetic field we are taking. Suppose that is value is B node. We have not calculated B node yet, but we are taking a averaged out value between A and B for a magnetic field and its direction. As per right hand screw rule, if we apply on this wire AB, then its magnetic field will rotate like this. Means in the right direction, magnetic field go into the page, or in negative z direction or minus k. So we will get the value of force on AB part is equal to, it will be I cross K will give us minus J, and minus J with minus sign will give us plus K plus J. So it will be I2 A B node J. Now if we similarly calculate force for CD, so it has the same current I2, but direction is reverse here. In AB, current was going in the positive x direction. In CD, current is going in the negative x direction. So A into minus I, and value of the field will stay the same as it is an infinite conductor. So in case of infinite conductor, at same distance, value of magnetic field stay the same. And AB and CD are at the same distance from this conductor, so value of magnetic field will stay the same, will be equal to B node. And direction is again same, minus K. And using solving this, what we will get, it will be minus I2 A B node J. This will be the value of forces on AB and CD. And using these, if we compare these two values, we can easily find out that both of these forces are equal and opposite. So FAB and FCD are equal and opposite, hence cancel out. So forces acting on AB and CD will cancel each out. Now coming to the force acting on AD and force acting on the CB. So now force on AB. Now at, oh sorry, not AB, AD. Now at AD, magnetic field is given by this formula, because here for AD distance stay the same, so we don't have to take any average out value. There will be single value, and that is given by this formula, and it will be, so first we write the value of current, that is I2, because force is IL cross B. Now its length vector will be in the downward direction, so we can say minus J, and length is A, so A with minus J, cross with the magnetic field. Magnetic field will again in the minus K direction, because these all conductors are in the same right side, and value of magnetic field will be here, this one. So mu node I1 by 2 pi of distance is A into minus K. So it will come out to be, A get cancelled here, and we will have mu node I1 I2 by 2 pi, and J cross K, negative is positive, and J cross K is I. For the remaining part, that is CB, FCB, it will be, current is I2, direction of current is change, so it will be now in the positive Y direction. So A J cross mu node, magnetic field will stay the same, 2 pi. Now distance, here we have a distance, and distance in this case is A plus A. The distance of conductor CB from the wire is A plus A, that is 2A. And here we have, we can say minus K. So solving these, this A get cancelled, and we will get half mu node I1 I2 by 2 pi with minus I sign, because J cross K is I and with negative sign. So as a whole, force on AD is in positive I direction. So force on AD is in this direction here, and force on CD is in the negative I direction. So net force on the loop will be vector sum of these, and these, as these both are in opposite direction, so they will be subtracted from each other. So net force will be mu node I1 I2 2 pi I minus half of mu node I1 I2 2 pi I. So it will be mu node I1 I2 by 4 pi with I, means this force is greater, and this is the repulsive force, this is the attractive force. So repulsive force is greater, so net force will be repulsive, and that is option C, and equal to mu node I1 I2 by 4 pi. Moving to the next one. A circular coil having n turns and radius r carries a current I. It is held in xz plane in a magnetic field B. The torque on coil due to magnetic field is. So here it is not mentioned that what is the value of what is the direction of the magnetic field. Suppose this is our plane, this is x, this is z, and here we have y, and we have circular coil with n turns, radius r, current I in xz plane. So suppose this is our coil of n turns, and as it is in xz plane, and suppose anti-clockwise current, so its we can say its magnetic dipole vector will be in the outward direction in y direction, as it is perpendicular to the plane, and magnetic dipole moment will be I into area. So current I into area is pi times r square, and if we have a magnetic field, then torque will be given by m cross b. So now we here in the question, I think direction of magnetic field is not mentioned. So, and okay, here we have a direction also, as we assumed it is counterclockwise, so its direction is j. So I pi r square j cross value of magnetic field is suppose b, and we can have we can say if we want to have torque here, then it needs to be in either magnetic field either needs to be in k or I. Only then we will have answer I pi r square b, and we have going to have n also here because n terms are there. And if magnetic field is also in the j direction, then 0 will be the possible answer. So either answer can be this, either option B is possible or option D is possible, depending upon the value of direction of the magnetic field. 0 will be when if magnetic field is in j direction, and this will be if magnetic field is in k or I direction. So moving to the next one, a infinitely long current carrying wire with a small current carrying loop in the plane of paper as shown. The radius of the loop is a and the distance from the center of the wire is d. If the loop applies force F on the wire, then we have to find out that what will be the value of the force F applied by the loop on the wire. And in this case, we can also say, as magnetic field is a conservative force, so force by wire on loop is equal to force by loop on wire. So both are exerting equal force on each other, and from that if we have to find force by loop on the wire, we can indirectly find it by finding the force by the wire on the loop, and force by the wire on the loop will be given by, for a wire this wire is exerting magnetic field here, so we have a formula for a current carrying conductor, force on a current carrying conductor by a magnetic in a magnetic field, that is given by F is equal to I L cross B. But this formula does not apply on a closed current loop because this is not a straight conductor. We need a straight conductor, only then we can apply this formula. And if we have some closed loop, then that loop act as a magnetic dipole. And for a dipole, we have a formula for force, and that is given by M, where M is a magnetic dipole moment of the closed loop, into dB by dx, where this is the variation of the magnetic field with respect to variation, we can say area or the distance occupied by the this loop. So first of all, what we assume, as it is at d distance from the we can say this wire, so it will be equal to magnetic dipole moment will be of this loop, assuming it has a current I1, we can say it has a current I1 suppose, and this has a current I. So magnetic dipole moment of this loop will be I1 times pi a square and now d by dx of the magnetic field. Now if this is the distance x, if this distance is x, it is already mentioned as d, we will put the value d after differentiation. Then magnetic field value at distance d from the wire is mu naught times current by 2 pi into distance, that is x. So it will become, after derivating, we will have I1 pi a square minus mu naught I by 2 pi x square, or we can say it like minus mu naught pi I1 a square divided by 2 pi. Now putting the value of x, and x is equal to d, so d square, or we can say force is proportional to a by d whole square, that is option D for us. Hence option D will be the right answer here. Moving to the next one. A charge Q is spread uniformly over an insulated loop of radius r. If it is rotated with angular frequency omega with respect to its normal axis, magnetic moment of the loop is. So we have to find out magnetic moment, and we know that magnetic moment is current times the area, and if it is if has a that coil has n number of rotation, then it is n times current times the area. So now let's slide it here. Now start. We have a Q charge rotating with omega angular frequency. So omega is equal to 2 pi times the normal frequency, and so frequency comes out to be omega by 2 pi. Means Q charge is rotating that much times per second. This is the number of frequency is number of oscillations per second, and in case of circular motion it is number of rotation per second. So Q charge is rotating that much times per second. So from that we can say current is flowing in the circuit is total charge flowing in unit time, that is 1 second. So it is total charge flowing in 1 second, and total charge flowing in the 1 second is equal to frequency times the amount of charge rotating in the one circle. So total charge rotating in the 1 second will be Q omega by 2 pi. This is the value of the current, and now we can find out value of, we can say, magnetic dipole moment. So it will be I times the area. Area is pi times r square. So Q omega pi r square by 2 pi. Cancelling, we will have Q omega r square by 2. So that is option A for us. And we can also solve this question using gyromagnetic ratio. In that one, we know that ratio of magnetic dipole moment divided by angular momentum is given by charge by twice of the mass. So magnetic dipole moment as it is m, angular momentum of a charged particle rotating in the radius of r is mass times its velocity times its radius is equal to charge is q and divided by 2m. Here's capital M is the magnetic dipole moment and small m is the mass. Small m get cancelled, and we know V is equal to r omega. So from this, m comes out to be q by 2 into V is r omega into r. So it is half omega r square, and we have q also, q by 2 omega r square, that is again option A. So we can solve it in the either way, whichever suits you better. Moving to next one. A uniform magnetic field B of 0.3 Tesla along positive Z direction. So field is positive Z direction. Sides are given and current is given. Out of the following different orientation, which one corresponding to stable equilibrium? Now, for stable equilibrium, the torque needs to be 0. For stable equilibrium, we know that torque needs to be 0. So, torque should be 0, and torque for a closed loop is given by m cross b. If m cross b is 0, means theta is 0 between magnetic dipole moment and magnetic field. So now let's find out. For this, for option A, the value of magnetic magnetic dipole moment will be in, we can say, according to right hand screw rule, as current is rotating anti-clock, so magnetic field magnetic dipole moment will be in the positive x direction. In this case, in option B, according to right hand screw rule, magnetic dipole moment will be in the negative y direction. As it is, you can use your right hand and rotate the fingers such that your fingers go into the screen, so your thumb will point in the negative y direction. And here in option C, value of magnetic dipole moment will be in the upward direction, so in the positive z direction, and in option D it will be in the negative y direction. So now looking at the angles, as magnetic field in the z direction, so in this case theta is 90 degree. In this case again, magnetic field in z direction and magnetic dipole moment in the y direction, negative y, theta is 90 degree. In this case theta is 0, as both are in same, and in this case theta is 180 degree. So this option C correspond to the 0 torque and stable equilibrium. Option D will have a 0 torque, but it is in unstable equilibrium. And option A and option B does not belong to any type of equilibrium. Here torque is maximum. In both of these options, A and B, torque will be maximum. Moving to the next one. Two coaxial solenoid of different radius carries current I in the same direction. F1 is the magnetic force on the inner solenoid due to the outer, and F2 is the magnetic force on the outer solenoid due to the inner. Then we have to find out their directions and also their magnitudes. Now, first of all, let's draw two solenoids. Suppose this is our smaller solenoid and this is the larger one. So we know that these solenoids act as a coils. They are in the they act as a coil because they resembles with coil. So they have some magnetic dipole moment. They have some value of m. And we know that for a magnetic dipole moment, value of force is given by m times variation of the magnetic field around them. Now let us consider this orange or smaller one solenoid inside the bigger one solenoid. We know that inside a solenoid magnetic field is constant. Inside this white solenoid, we can say if their current is I, then B, and considering it is as solenoid number 1, so B1 will be inside this solenoid mu node Ni, and this value will stay constant. So if value of magnetic field around this orange solenoid or second solenoid is constant, means dB by dx is equal to 0. So force will be 0. And we know that both of the solenoids will exert equal force on each other. So force by white on the orange is equal to force by the orange on the white, and we know that force on the orange by white is 0. So reverse will also true. So option C will be the right answer here. Now moving to the next one. A rectangular loop of side 10 and 5 centimeters, current of 12 ampere placed in a different orientation as shown. If the uniform magnetic field of 0.3 Tesla in the positive z direction, in which of the orientation it will be stable, unstable, and that is. So we have to again explain. I think this question is the same as we just solved here, like this one. So let us do it in a quickly manner. So here in this one, the value of magnetic dipole moment will be in the positive x direction. Here value of magnetic dipole moment in the negative y direction. Here value of magnetic dipole moment will be in the positive z direction, and here magnetic dipole moment will be in the negative z direction. So if we write values of theta, in this case theta is 90 degree. Here again theta is 90 degree, and we are taking theta between magnetic field and the magnetic dipole moment. Magnetic field in the z direction, here dipole moment in the x, so x and z angle is 90. Again here y and z angle 90. Here both are in z direction, so angle is 0. Here both are in opposite, so angle is 180. So this represents, with theta is equal to 0 is stable equilibrium condition. This is stable, 180 is unstable. So option B comes in stable and option D comes in unstable. So option A here is B is stable and D is unstable. Moving to the next one. Two long straight parallel wires carrying adjustable current I1 and I2 kept at a distance d apart. If the force F between the two wires is taken as positive when they repel each other and negative when they attract each other, the graph showing the dependence of the force on the product of their currents. Now force acting per unit length in two parallel conductors is given by mu naught by 2 pi I1 I2 by their distance. Now suppose they have force, we can say their current is in same direction. If their current is in same direction, it can be either, we can say, both upward, and it can be either both downward. So both upward will be taken as positive, both downward will be taken as negative. So again negative product is positive, positive product is positive. So force will be positive, and we know that when both are in the same direction, current in the same direction, they attract each other. So when product of I1 and I2 is positive, they will attract each other. And here it is mentioned that if they attract each other, then we have to take it as negative. When both wires are attracting each other, then force needs to be negative. So force is negative when I1 and I2 product is positive. So here in this region we have I1 I2 as positive, so force needs to be negative here, and here we can say in option B, force is positive when I1, I2 are positive, so this option gets rejected. This option also gets rejected, so we have option A and C left. Now coming to the, when product of I1 and I2 is negative, means their current is in opposite direction, and if their current is in opposite direction, they will repel each other, and when they repel each other, we have to take force as positive. So when I1 I2 product is negative, force needs to be positive, and that we can find in option A. So option A will be the right answer here. So with this, we end this video here. Hopefully what we have covered till now is helpful to you and understandable also. Again, if you have any doubts or suggestion, you can put them in comment section. I will try to solve them. And if you find these videos useful, then do press the like button, share them, and subscribe to our channel. Also, if possible, do make some donation by scanning these QR codes. So with this, again, thanks for watching, and we will meet in next video.